The next experiment is to study the physical principles and the technology of a laser. The experiments which will be covered here: first, the setting of the cavity to obtain the lasing effect. Second, to study the stability conditions of the cavity. Third, to study the transverse modes of the lasers. Fourth, the effect of polarization, the study of polarization of the laser beam. And finally, the study of the spectra of the laser radiation. First, we'll discuss about Einstein's theory of the atomic transitions. Let the number of atoms per unit volume in the ground state, that is then when the energy is 0, be by En0, and the numbers of per unit volume in the excited state at some energy E is N. Then we know that N is equal to N0 exponential minus E by kT, where K is the Boltzmann constant and T is the absolute temperature at which the transition occurs. So from this equation we can see that the number of atoms per unit volume in the ground state will be many greater than that in the excited state. Now suppose there are two atomic states of energies E1 and E2, and N1 and N2 be the number of atoms per unit volume in that energy states. So from the equation N is equal to N0 exponential of minus E by kT, if we put N2 here in place of N, and if we place N1 here in place of N and divided it, so we will get N2 by N1 is equal to exponential of minus E2 minus E1 by kT. Now in E2, that is the second excited state, it is greater than E1, so naturally N2 will be less than N1. So in the energy states, the maximum number of atoms per unit volume will be in the ground state, and it will decrease gradually. So in the first excited state, the number is less than the ground state, and in the second excited state the number is even lower than the first excited state. Now we are considering only the two states, one is E1 and another is E2. So now E2 is the higher energy state and E1 is the lower energy state. So there will be a spontaneous transition from E2 to E1, and the rate of the transition will be determined by N2, the number of atoms per unit volume in the state E2, and the probability of the spontaneous transition, which is A to 1. So what is A to 1? So A1 is the probability of the spontaneous transition from E2 to E1. So the number of transitions per unit volume per second will be A21 N2. Another transition occurs when the energy is absorbed by E1 state and it will move to E2 state. So what is the energy, what would be the EM radiation of to perform this transition? The frequency should be E2 minus E1 by h, where h is the Planck's constant. So rate of that transitions will be a function of N1, the number of atoms in the per unit volume in the E1 energy state, and the energy density of the radiation, which is U nu. So number of transitions per unit volume per second of that kind would be B12 N1 U nu. And the last kind of transitions is called the induced transitions, because the energy is absorbed and it is induced and induced to the upper states of the energy levels. And besides these transitions, another types of transitions is stimulated emission. So there would be a downward induced transitions from E2 to U1 by applying the EM radiation to the E2, and it will result a stimulated emission, and the frequency would be E2 minus E1 by H. So that rate would be B2 per unit time and unit volume would be B21 into U nu. So where B21 is the probability of such transitions. So we have got three coefficients. One is A21, one is B12, and finally B21. So A21 is for the spontaneous, A is for the spontaneous transition, and B is for the induced transitions. So A21 means the spontaneous transitions from state 2 to 1, and in the induced transitions are B12, so from state 1 to state 2 by by absorbing the photon, and with the application of the induced radiation, downward in downward stimulated emissions happens, and that coefficients is B21. So these are the Einstein's AB coefficients, and under equilibrium condition, this downward rate and the upward rate should be equal per unit per second per unit volume. So we can say that A21 N2 plus B21 N2 U nu, it would be equal to B12 N1 U nu under the equilibrium condition. So from here we can say that U nu would be A21 N2 by B12 N1 minus B21 N2. So from here, with if we do some algebra here, so and by putting the value of N1 by N2, we'll get A21 by B21 into 1 by B12 by B21 exponential H nu by KT minus 1. And from Planck's law, Planck's radiation formula, uh, we know that U nu is equal to 8 pi h nu cube by c cube into 1 minus exponential of h nu by kt minus 1. So comparing these equations, the Planck's radiation formula, and which equation we get from the equilibrium condition, we can convert that B12 is equal to B21, and A21 by B21 is equal to 8 pi h nu cube by c cube. So in the year of 1917, Albert Einstein did these calculations and calculated the probability of the transitions between the atomic levels. The full form of laser is, as you know, that light amplification by stimulated emissions of radiation. So as the name suggests, light is amplified. So light is amplified through which phenomena? Through the stimulated emission of radiation. So the mechanism of the laser is actually based on uh, the Einstein's theory, which was uh, calculated by Einstein, the transition probability of the atomic levels. So in the figure B, the spontaneous transition of an excited from an excited to lower energy states is shown here. So in that case, we know that when the spontaneous transition occurs, a photon comes uh, due to the transitions. So this can be the source of the light, and the lifetime of an atom to exist in the uh, excited state is the order of 10 to the power minus 8 second, and the energy of the photons emitted from the spontaneous transitions would be E2 minus E1, and which will be h nu 12, where nu 12 is the frequency of the emitted photon and h is the Planck's constant. Now when h h nu 12, which is equal to the difference of the energy levels E2 minus E1, it is incident on E1, so the upward transition occurs from the lower atomic level to the upper level by absorption of that photon. And in the spontaneous transitions, when the photon is generated, so it is actually the incoherent in nature. That is its phase is random. But in the case of induced transition from excited state to the lower state, so the incident photon, which has the energy of h nu 12, which is equal to u2 minus e1, and due to the transition, a photon is emitted, and which has actually equal energy of the incident photon, and further it has the same direction as the uh, and the phase is same of the incident photon. So two coherent photons is generated due to these induced transitions from the excited state to the lower state. So if these two coherent photons which is generated due to this phenomena, it is incident uh, in another two atoms, then it will generate four such coherent photon which has the same phase difference and which has the same direction. And again these four coherent photons will be bombarded into another four atom, and another such four transitions will occur, and therefore 8 photons will be generated which will be coherent in nature. So it is a cumulative process, and the production of such photons will be in chain, and the light will be amplified sufficiently to form the lasing action. For the amplification of the light sufficiently and for the lasing action, the condition is that the upper energy state that has the energy E2, it should have sufficiently increased atoms. As we know that due to the Boltzmann equation, the lower energy states has many uh, greater atoms per unit volume that in the high energy states. But in this condition, to form the lasing, the upper energy level should have sufficiently increased atoms per unit volume. That is, N2 should be greater than many greater than N1. So there are number of ways to do so. So that is called population inversion. So normally the lower energy states have the greater atoms per unit volume, but it should be the inverse. So the population should be inverse. That is, the higher energy level should have more atoms per unit volume. So that is called population inversion. So there are a number of ways to do the population inversion. One of them is optical pumping. When with the help of the photon, we can achieve this population inversion. Another way is excitation by the electrons. That is called that is the method. The electric discharge, due to the electric discharge, the and the excitation by the electrons will cause the population inversion. Another is inelastic collisions between the atoms, and another way is the excitation by the chemical method. And as the excited state has very low lifetime, so it is of the order of 10 to the power minus 8 second, there will be always a spontaneous transitions there. So we should have a metal stable state which has a greater lifetime. Now helium neon laser cavity. So in the picture of the laser cavity, it is shown a helium neon laser. So there is a discharge tube here, and there the helium and the neon gases are filled with a particular proportion, with a particular ratio. The ratio of the mixture is 7:1. So 7 is for helium and 1 is for neon, and it is kept under very low pressure. So two mirrors are there, two curved mirrors are there, which has a radius of curvature, and in the front, in the back end, it is a mirror is attached, and a moving mirror, and the front mirror can be moved in the optical bench. So, and two windows are used, that is called the Brewster's windows, and it is inclined at an angle of the Brewster's angle, that is theta is equal to tan inverse n. So in the plane of incidence to be transmitted through the two windows, so that a particular so that the light is polarized in a particular plane, and a plane polarized light can be come out. So the produced laser would be the plane polarized light, plane polarized laser. So between the two electrodes, a high voltage is applied, and due to the discharge of the tube, a, the light is produced, and it is getting amplified due to the uh, cumulative reflections, and a highly collimated and high intensity light beam is produced through the laser cavity. Now look at the energy levels of the helium and neon. So the 21s and 23s are the metastable states of the helium, and due to the electric discharge, the some helium atoms are transmitted are raised to that metastable states. And as these metastable states have a longer lifetime, the optical transitions to the lower states, it doesn't happen, and the numbers in that metastable states it is getting increased. And you can see that the 3s and 2s levels of the neon are slightly lower than the helium states, the metastable states of the helium. And due to the collisions with the helium atoms and with the neon atoms, the atoms are raised to the excited states of the neon atoms, leading to the population inversion in the neon atoms. And when the transition occurs in the neon atoms from the excited state to the lower energy state, that is 2p or 3p, the laser beam is generated with different wavelengths uh, depending on the transitions. So when from 3s2 to 2p4 this transition occurs, so we'll get 0.6328 microns or 632.8 nanometer laser source, and due to the other transitions we'll get the different wavelengths. So here we can observe the production of 632.8 nanometers lasers in our experiment because it is in the visible range. So we'll see how the laser beam is produced in the upcoming lab demonstrations. Thank you.